Here we go. We're recording.
So we're going to reuse the same notebook that we
You have to have a new one.
for next year.
Yeah. But it's only $1. Let's see. Oh, here we go. Okay. Just a little housekeeping. Today, all we're going to do is review for the Exam7, Chapter 9, which will be on Monday the 9th at the regular time. As far as the lab goes, the last lab exercise report on the molecular weight by the Dumas method is due today. And I've got, I think 3 came in on Blackboard already. Let me check to be sure. Yeah. I've got 1 for Carpenter, 1 for Lee, and 1 for Maul. Okay, if you, I'm not going to chase anybody around trying to get you to turn in your late stuff. So if you go on Blackboard and check your My Grades, if you don't see a grade in there for something, then that means you're missing a homework item, or for the lab, both. As far as the lab notebooks go, next week when we meet for the last exam, I'll pick them up during that period and hopefully get them back to you before you leave so I don't have to keep them in my office. Okay, let's look at Chapter 9. That out. That one out.
I guess it would have been 2 weeks ago when me and Cordell were trying to log on. It just said there was no class during this time period. So I checked for like
For Zoom?
Yeah, I checked like 2 or 3 hours straight, and it just kept saying no class available during that time. I went to your actual course thing first, and then I clicked on Zoom there,
Yeah.
where it would bring you right to it.
Yeah.
It still wasn't doing anything.
I think I know what happened. I was testing out the cameras, and I did a short recording using that link. And I think it decided that when I was finished with that link, that the class was no longer available. I think that's what happened. I didn't count you absent, though.
Okay. Yeah, well, I went on there and watched it.
Okay.
It said there was nothing on there, and I was like, oh.
Yeah. I'll remember not to do that again. Or if I do want to do a camera test, I'll do it without logging into our regular course.
Yeah. Do you have the Chapter 9 PowerPoint by any chance?
Yeah, got everything here.
I guess a Word document too. Yeah. Thank you.
All right, so let's get down to business here. I invested in some markers so we don't have to keep swapping out.
They new markers.
Yeah, I had to buy my own. I put in an order, you know, but they haven't produced them yet, so we can't wait.
Typical stuff.
We can't wait for management, you know. We gotta get this job done. Okay, let's see. Well, as usual, you guys probably don't have any questions because you didn't, unless you got online and you got the review document ahead of time.
Yeah, I did not get the review document yet. I
Okay,
did watch the class online, the pre-recorded lecture though.
all right. So, well, if you have any questions, we'll start off like that. Otherwise, I'll just jump in and start working problems. As usual, if you know what useful information is going to be on the exam, just look at the back of the review document. You'll see the pages that are going to be there.
Wait, you said what's going to be
The last pages, useful information, those very last pages that I always put on the review document,
on? Oh,
those will be on the exam. Okay. I'm just reminding everybody. It'll be mostly multiple choice, but there are some short answers. And we'll look at some of those short answer types today. Okay, so we're this chapter focuses primarily on covalent bonding, and it begins with a modification to the localized electron model called hybridization. Right. So what does hybridization mean? Well, if you remember, the localized electron model says that electrons belong to each atom, and you get bonding by sharing those, but they still are basically belong to one atom or the other. It's just they spend part of their time between the two. So what that means is that the sharing takes place by overlap of orbitals. Right? So we're still talking about a localized electron model. And as long as you can get orbitals to overlap and produce the desired three-dimensional or geometric structure, then you're fine. But the problem arose when we actually got physical experimental evidence for the structure of molecules and found that they didn't match the simple overlapping of orbitals. All right, so we had to make a modification, and we did that by hybridization. So the example that I gave in class was methane, I think, or maybe carbon tetrachloride would probably be better. Okay. So if we use, and we've already gone through the VSEPR model, valence shell electron pair repulsion. So we know that if you draw your Lewis dot structure, which is where you start, right? So you have 4 valence electrons there, and you have 7 each here. So for 28, so that equals 32. Right, and then you do like that, 2, 4, 6, 8. Right, so that's 24, right? So you have 24 electrons that go around here. And you start from the outside and work your way in. Right, so you have 4, and you divide 6 into that, then 6 electrons each. That would give each one an octet. Okay, so what does 4 electron groups tell you about the geometry around this carbon atom, tetrahedron, right? So you're going to be looking at carbon in the middle, and then you have a chlorine here, and a chlorine here, and a chlorine here, and a chlorine in the back. Right? So you have your tetrahedron there, your four-sided. The problem is that when you look at the valence structure for carbon, remember how we do the atomic structure, electronic structure for carbon, we have 1s2, 2s2, 2p2, right? And the valence electrons are these four. You've got 2 in p orbitals and 2 in s orbitals. That does not give you tetrahedral symmetry, right? Because when you overlap these spherical orbitals, they can happen anywhere, right? But the p orbitals are directional, like this, right? You could get something approaching a tetrahedron if it was only p orbitals, but we don't. We have s orbitals and p orbitals. So the solution to that problem is you need these 4 valence electrons because they're shared here. There's one there, one there, one there, and one there. And then the other one comes from chlorine, right? So you need these 4, but they cannot operate in this structure as S and P separate, right? So you hybridize them. You have 3 p orbitals and 1 s orbitals give you 4 equivalent orbitals that are directional in a tetrahedron. Okay, and that hybridization is a modification to the localized electron model that gives us that answers the question. That gives us the tetrahedral structure and can be accounted for in the electronic structure. Okay, so that's why the hybridization was developed, and then it continued to blossom depending on where it was needed. So maybe you ought to work some problems and then rather than just regurgitate the lecture, we'll look at some problems. Let's see. I don't think this document is set up quite like I usually do, with the easy ones in the front, the hard ones. It's really just a mix.
May I ask a question, Mr. Black?
Sure.
You had a version 1 and version 2 on the laptop. Is that?
This one's version 1.
Okay, thank you.
You probably do well to look at version 2 also, because I could draw those types of questions for the exam from version 2 as well. What I tried to do is split it up into 2 versions because the original version I had was just a monster. You think this is bad? The original was worse. So I tried to split it up so that you had the same types of problems in each document, but there's maybe 80% overlap. There might be some unique type problems in version 2 that you don't see in version 1. So just skim through it and see if you, after you've gone through version 1, then you should be able to just take out version 2 and look at it and say, that wasn't in version 1, study that one. Okay. Why don't we go to page 12 and look at those short answers, because they give us some definitions that will help with some of the other problems. Okay, 49. The CCH bond angles in ethylene. So ethylene is C2H4. This is 49.
49?
Yep.
Oh, cool.
So then you wonder, all right, what kind of bond is between those? Well, if you just put a single bond, you don't have an octet for carbon, right? So we need a double bond. Now you can prove that to yourself by just taking C2H2 and draw the Lewis dot structure. And it will give you that molecule. So the bond angles for this are given as 120 degrees. So that means this angle, that angle, that angle. They're all 120 degrees. So what does that tell you? That tells you this is trigonal planar. That's the only way you can get 120 degree bond angles out of that molecule. So what's the hybridization here? Well, how many? Okay. We talked about this in class. When you have a double bond, one of them can be a sigma. What type of bond is a sigma? It's always on axis between the atoms. That means you can only have one sigma bond. If you have a second bond, it can be a pi bond, which is off axis. Okay? You can have two of those around the molecule. So you have one sigma, one pi. So if you have 3 sigma bonds, that begs the question, what hybridization do you have? Well, if you need 3 equivalent sigma bonds, you need 3 original atomic orbitals to hybridize. You always start with the S, and then how many P's do you need? You need 2 P's. So that gives you 3 bonds, and 3 of those gives you this symmetry. So a trigonal planar, where you have 3, well, by the VSEPR model, you have 3 groups, right? 3 electron groups. 3 electron groups means sp2. Okay? Did I put that chart up on the board during the lecture?
So 3 electron groups equals 3 sp2, so do we just need to put sp2?
sp2 hybridization, yeah. This just means that you get 3 of them. And
3 of those mean that, same thing?
yes.
Okay.
When you hybridize orbitals, the atomic orbitals that go into making up the hybrid orbitals, you have to have the same number coming out as go in. So if you have 1 s and 2 p's going in, you got to have 3 sp2s coming out. 3 go in, 3 come out. So if we have 3 groups, before we had our original talk, sp3 hybridization, that's 4 electron groups. This is trigonal planar. So this one was what, tetrahedral. And what could we do? SP, right? You can have 2 groups, 2 electron groups. That would be linear. Okay. What if you have 2, 3, 4, 5 electron groups? Oops, we ran out of P's.
We go to the D's now?
Right, get a D. Wait a minute, the way they write it, the convention is put the D's in front. DSP3. And what would this one be? If you have 5, you would have 3 in a triangle, and then 1 at one apex and 1 at the other apex, which would be trigonal bipyramid. And then the last one that we investigated was where you had 6 electron groups, you need 2 Ds, 1 S, and 3 Ps. And 6 groups means octahedral. Okay? Now this symmetry is electronic. If you're looking for molecular symmetry or geometry, right, you have to do this one first. And sometimes these hybridized orbitals don't give you a bond. That's the real trick to using this. If you've got bonds, fine. This symmetry is the same as molecular. If every one of them is bonded. But if you have one with a lone pair in it, then you have to cover up that lone pair and say, then what is the molecular geometry? And we have some problems in here that will deal with that. Okay, so 49 was sp2. The mixing of native atomic orbitals, 50, to form special orbitals for bonding is called hybridization. We discussed that. this definition, 51 gets into the molecular orbital. Discussion. So we'll just say a bonding molecular orbital is lower in energy than an atomic orbital of which it is composed. And that goes back to the, where you have energy here, and you have, let's keep it simple. Let's say you have one hydrogen atom here, one hydrogen atom here, and you start off with one s orbital here and one s orbital there. Right, those are the atomic orbitals. The molecular orbitals that you can produce in these have to be the same number. You got 2 going in, you need 2 coming out. So we produced a sigma made from 1 s's and a sigma star made from 1 s. That's an anti-bonding. This is a bonding. The bonding orbital, I think it's safe to say that the bonding orbital is always less than the atomic orbitals of which it's made. Sometimes if you had a different atom over here, this is homonuclear, right? Because both nuclei are the same, from the same element. But if you had something else here besides hydrogen, say you had a fluorine, then it would start off different levels. And then the combination would give you an anti-bonding up here and a bonding down here, but the bonding would still be lower than the atomic orbitals that made it up. Okay, so that's the number 51. A bonding molecular orbital is lower in energy than the atomic orbital from which it was derived. This one's always lower, this one's always higher. But you always have the same number. 2 here, 2 there. And this is, these are the atomic atoms. This is the molecule. These belong to that molecule. These belong to the atoms that go into before bonding. So if you start off with 1 electron each here, then you start filling them up from the lowest energy up, like that, okay? So this is the molecular orbital for that molecule. Molecular orbitals do not belong to individual atoms. Localized electron model, electrons belong to individual atoms. But in a molecular orbital, the electrons belong to the molecule. And we construct molecular orbitals to insert our electrons. Okay? So while we're here, what's the bond order of this molecule? Remember how to calculate bond order? It's the bonding electrons minus the anti-bonding bonding electrons divided by 2.
So it'd be 11 minus 0.
It'd be 2 minus 0
I'm sorry.
divided by 2 equals 1. Okay? Now, what if we made an ion out of that? Let's say we ionize that one, give it an extra electron. Where is that electron going to go? Can't go here. That one's full. Got to go there. Right? So the bond order of this molecule would be 2 minus 1 divided by 2, which is 1/2. And as a general rule, the higher the bond order, the stronger the bond. Right? So this one is a stronger bond than that one. When we added that electron, we weakened the bond. If we took one away, right, 1 minus 0 divided by 2 is 1/2. So in this case, adding 1 weakens it, subtracting 1 weakens it. That's not always the case. Sometimes adding an electron strengthens the bond. The only way to know for sure is to do the molecular orbital structure, calculate the bond order. Okay? Let's see, 52. The number of molecular orbitals formed is always blank the number of atomic orbitals combined. The same number of molecular orbitals as the atomic orbitals that went in to make them up. You start off with 2 atomic orbitals, you got to have 2 molecular orbitals. We just did 53. Bond order is the difference between the number of bonding electrons and the number of anti-bonding electrons divided by 2. Okay, let's see. 54. Blank causes a substance to be attracted into the induced magnetic field. What are your choices there? You have 2 choices. They're prefixes to magnetism. Paramagnetism is the answer to that one. Diamagnetism is the other one. So paramagnetic versus diamagnetic. Molecules that are paramagnetic are attracted. This is external field. External magnetic field. These are attracted into it. These are not attracted. Not attracted or repelled. Okay, and that can be measured. We have very sensitive instruments that can measure this, whether it's attracted or not. Why do we need to know that? Well, actually, the phenomenon was noticed before we had an explanation for it. The explanation is in terms of paired versus unpaired electrons. If all of your electrons in your molecular orbitals are paired, it will be diamagnetic. Right? Because remember, when they're paired remember it like that, one spinning one way, one spinning the other way, and they cancel each other out. Because a spinning and moving charge generates a magnetic field, always. So if it's spinning, it's just sitting there spinning, it's moving, but it's generating a magnetic field one direction, the other one's spinning the other direction, its magnetic field is opposite. They cancel each other out. So there's no magnetic field to be induced and cause an attraction. into an external field. But if you have unpaired electrons, that's one electron or more that is generating a magnetic field that's not matched by any other electron in the molecule. So we use that information to tell us something about the molecular orbital structure of molecules. If we propose a molecular orbital structure and our proposed structure says this molecule should be diamagnetic, but we put it in a magnetic field and find that it's paramagnetic, that means our model is wrong. It has to be modified. Okay. So you remember which modification we talked about? I think I have at the end of the document, we have some information about, yeah, the last page. And the discussion of diamagnetic versus paramagnetic was central to the interpretation of SP mixing. Remember what SP mixing is? The most basic definition is that if the atomic orbitals of the atoms that go into a molecule are close enough in energy, the S's and the P's are close enough in energy, then they will mix, and the order of the molecular orbitals will be flipped. It won't be what you expect. But if they're far enough apart, then you won't get SP mixing, and then the molecular orbital that you propose, that you would normally think is correct, is the right one. And the reason we know that this happens is because of that phenomenon of paramagnetism versus diamagnetism. So if we look at an example, let's see. Oxygen would be a non-mixing. So if you have O2, and this is derived from the individual oxygen, well, I might as well do the whole thing. So we're starting out with oxygen atoms, and we're only going to look at the valence electrons in oxygen, right? So what would they be? Well, since oxygen is in the second period, we're talking about 2s and 2p orbitals. The 1s's we just leave out because they're not involved in the bonding anyway. So we would set up our structure here as we have a 2s, let's see, somewhere right in here, for both of them. And then we have 2 P's, 3 each, right? Okay. So this one's easy. Just put these together, and we get a sigma star and a sigma, derived from 2 S's. Okay. Oh, by the way, how many electrons are we starting with? 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay. So we've got to take 2, 4, 6, 12 electrons and put them in our molecular orbitals. Okay. So when we create sigmas and pi orbitals here, remember we can only have 1 sigma orbital and 1 sigma star out of these p's. The rest have to be pi's. So what we propose, and this is no SP mixing. So if you look at the periodic table, no sp mixing occurs here over for the homonuclears, O2, F2, or S2, CO2. Over here, you get mixing because the s and p orbitals are close enough together. But over here, they're far enough apart, so you don't get any mixing. So our proposed here, here, like that. So 1, 2, 3, 4, 5, 6. Oops, sorry, too many. Now we're going to let me get away with it. Right. So that's what we would expect. We would expect a sigma from the two p's here and a sigma star way up here. And then this would be a pi and a pi, and a pi star, and a pi star. Right, leave both of these from the two p's. That's maybe 2p, let's see. This was formed from the x, so this would be a y, and this would be a 2pz. Y and a z. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You have the same number of molecular orbitals. And without mixing, you have both the sigma and the pi's first. And then you get the pi's, sigmas, stars on top. But if you have mixing, you would get an inversion of, let's see. You would flip these two right here. You would still have these up here, but you would flip those there. And what that does is, as you start to fill up, they fill differently because you have to fill these two first if there's mixing to get to that one. But for oxygen, we have, what did I say, 12 electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so what should we expect from this one? Its magnetic properties. We've got 2 unpaired electrons here. It doesn't matter that they're in antibonding orbitals. The only thing that matters for magnetism is, are they paired or unpaired? These are unpaired, right? So oxygen should be paramagnetic. And in fact, it is. The example I use is, seen those big horseshoe magnets? Right? Some of them are huge. They work best. Very strong magnetic field between the two prongs of the horseshoe. You take liquid oxygen and pour it into that gap. Some of it goes through, but most of it sits right there in the gap. Right? It responds to the magnetic field because of these. Now, what would happen if there were mixing? Well, we'd flip these two, and then with this many electrons, you'd get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would still be paramagnetic. Doesn't matter for oxygen. But some molecules, it does matter. In fact, I think one of the questions, here we go, yeah, number 61. So we've done oxygen here for number 61. We haven't done nitrogen. 61 says, draw a molecular orbital diagram for oxygen and nitrogen. Explain why the removal of one electron in oxygen strengthens bond while the removal of one electron in nitrogen weakens the bond. So we might as well take that and draw the nitrogen. So we've got the oxygen. Let's do the nitrogen. Now nitrogen is going to have mixing. And so that you don't have to memorize all this garbage. I'm not trying to turn you into chemists. I just want you to understand what you have is, let's see, useful information should be. Oh, we're just on it. Last page. See, so you've got the thing right there. You just have to be able to draw it and use it to explain, answer the question. Right, so drawing it is almost a gimme. Okay, so nitrogen is going to have 5 valence electrons each, whereas oxygen has 6, makes 12. So 5 times 2 is 10. Okay, we got 10 electrons we have to put in there. Okay, this part is going to be the same. Got a 2s and a 2s, and then we have 2 p's. Right? So we get a sigma star derived from the 2 s's. And then this one we get an inversion because of mixing. So instead of having a sigma down here, we have 2 pi's, and our sigma goes up here. And then our pi stars stay put, and our sigma star stays put. Okay? Okay, so now we got to put 10 electrons in there. We started off 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. And we got to put 10 in here. So there's 2, 4, 5, 6, 7, 8, 9, 10. So should nitrogen be diamagnetic or paramagnetic? Does it have any unpaired electrons?
Well, yeah.
Here we go, 2 unpaired electrons. Okay,
Oh, yeah.
did I draw that right? No, I didn't draw that right. 2, 4, 6, 8, 10. I put too many in there, didn't I? 2, 4, 6, 8. Oh, sorry. Too close. You see what I skipped right over this sigma. Right, so 2, 4, 6, 8, 10. Okay, so you were right the first time. Diamagnetic. Because they're all paired. There's a pair, 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 and a pair. And here we got a pair, and 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 unpaired. Okay? Now, how do we answer this question? Well, the conditions, after you draw those, using the molecular orbital theory, explain why the removal of 1 electron from oxygen strengthens, while the removal of electron from nitrogen weakens. All right, so let's do it this way. What happens when we remove an electron? That makes 1 positive charge here, right? 1 positive here. That removes an electron. But before we do that, how are we going to explain the strength of the bond in a molecular orbital environment? Bond order. You have to calculate the bond order. So the bond order here is bonding 2, 4, 6, 8. And then minus 2, that's it, divided by 2 equals 3. So the bond order for dinitrogen is that. The bond order for O2 is what? Well, there's there's bonding, 2, 4, 6, 8, 10. All right? And then anti-bonding, 2, let's see, 2, 4, 6, excuse me, 8. Thank you. 8. And then anti-bonding is here, 2, 4, right? Okay, so it's bond order. Before we do anything to it, we start with 3 here and start with 2 there. So if we subtract an electron, where does the electron come from? For nitrogen, you subtract an electron, it comes from a bonding orbital. Right? So this one would be 8 minus, 7 minus 2, excuse me. Take 1 from the bonding orbital, minus 2 equals 2.5. But if we take 1 from oxygen, where does it come from? It comes from an anti-bonding orbital, right? So the O2 with 1 removed is 8 minus 3, which is equal to 2.5. Right. So dinitrogen starts out stronger than dioxygen. But when we remove an electron from nitrogen, makes it weaker.
Is the reason why you moved it from the was because of the diamag?
No, that has nothing to do with it. It's purely bond order. We calculate the bond order of the unmodified dinitrogen as 3. 8 minus 2. You only have these 2. Let's see, where are they? 2. These 2 anti-bonding here, and the rest, 8 bonding, gives you a bond order of 3. So when you remove 1 electron, where does it come from? It comes from the highest energy level.
Oh, because it's bigger.
Right, so you move down until you find one. Okay, here. This one comes from a bonding orbital. So that makes this one, instead of 8, 7, gives you 2.5.
Oh,
So we weakened it.
It comes from the first, the largest one on top.
Yeah, start from the top.
That's why that one.
Right, you come down here, you take 1 from the antibond. So that means 8 minus 3 instead of 4 gives you 2.5. So by removing an electron, for dinitrogen, we've weakened the bond. And for oxygen, we've strengthened the bond. So their bond orders tell us that they should have approximately the same bond energy at this point. This cation and that cation should have the same bond energy, take the same amount of energy to break the bond. It may vary a little bit, but not much. Okay? That answers question 61. You just have to put it in words. Okay, any questions about that one? We're just sort of, I guess we're sort of stream of consciousness. We've gone from hybridization right into molecular orbitals. Okay, let's see. Well, while we're back here, let's see if there are any other short answers that we can deal with. Okay, how about number 60? Number 60 says we have 3 molecules. Molecule A, B, and C. Okay. I'm going to talk about the molecular structure. As technically speaking, this is electronic. But we don't have any lone pairs in there, so they're synonymous. What type of hybridization? And let's see, before I forget, are we still in focus, Kyle? Okay, good. All right. Hybridization, bond angles, and an example. Okay. Got those, that. Okay. Let's see. We're given this one. All right. Let me change the colors. About red. And then you look to the description to fill in the rest of the information. Okay. So consider 3 molecules. Molecule A has sp3. Okay, we got that in there. Molecule B has 2 more effective pairs. So let's fill this one in first. Believe it or not, if we know that it's sp3 hybridized, we can fill in the rest of this. sp3 is what structure? Tetrahedron. Or tetrahedral. That's fine. What's the bond angle in a tetrahedron? You just have to memorize that one. 109.5 degrees. Is that red showing up, Kyle? Is the red showing up okay?
Yeah, for the most part.
Okay, maybe I better pick a different color. Yeah, where are you located?
What do you mean? At home?
Yeah, what school is he from?
Like, which one does he go to? Did you go to the one over in Red Rock County? I think we have math.
Oh,
Yeah, I think it's kind of from that.
are you zooming in because of weather?
No, car problem.
Oh, okay, okay. So let me write this in a better color. Red doesn't show up too well, so we'll try brown. Brown's better, isn't it?
Yeah, it looks better.
Okay. Bond angle is 109.5. And what's an example? Well, we did one earlier, right? Yeah. The one we did earlier was carbon tetrachloride. Methane works. You know, anything that's got 4 atoms attached to a carbon will give you a tetrahedron, basically. We could change the chlorine to fluorine. Same thing. Okay, so now the next bit of information will tell us what B should look like. B has 2 more effective pairs, electron pairs around the central atom.
So just add to your sp3, so you get 5 sp3, change it to D.
Okay. 2 more pairs, right? So what does that mean? That means bonds, right? You got 2 more bonds. So if you've got two more bonds, you need two more hybrid orbitals, right?
Why would we keep two? Could we just D?
No, because D only gives you one pair. Remember, a pair equals a bond, right? So two pair requires two more orbitals. Okay, so what's the structure for this one? 2, 3, 6. Octahedron. Okay. So what are the bond angles for an octahedron? Well, you kind of have to visualize the like that, and then you've got something up here, something down there. So you got 1, 2, 3, 4, 5, 6. Right. So what are the possible angles? Well, you could have angled from this one to this one, right? Would be 180 degrees. This one to this one, like from the central atom, would be 90 degrees. Or from this one to one of these would be 90 degrees. Those are the only possibilities. I don't see any others. So the bond angles for this one would be 90 and 180 degrees. Okay, what's a possible example? Well, if you're going to have 6 of anything bound to a central atom, you're probably going to have to move down. Well, you have to move down to pick up a d orbital. It's got to be here or here, usually. And a good example is take sulfur and bind 6 of anything to it.
That works.
That's a good example. Yep. Okay, C. Molecule C consists of 1 sigma and 2 pi's. So this one has 1 sigma and 2 pi's. So what does that mean? Well,
This has 2 pairs. Like 1 pair, because it has a pi and a sigma.
yeah. So a pi and 2 sigmas means a triple bond.
I can just, that can be one whole thing as well. Never mind.
Okay. If you had 3,
It could be 2 on one side and 1 on the other.
if you had 3 like that, that would be 2 sigmas. But you can only have 1 sigma. Okay.
Sorry.
So 1 sigma and 2 pi's means that you've only got 2 atoms in that molecule. So it's linear.
Sorry.
And in order to get it hybridized, you need sp, 1 from each side. So one will give you an s, the other give you a p, hybridize the orbital. Well, actually, no. You would hybridize an sp in order to give you let's see. Well, linear, right? Linear is always sp, right? sp2 would be what? sp2 would be trigonal planar, right? That one wasn't in here, but sp is linear always. So there's only one possibility there. Now, what can we do about an example? Well, you just need 2 atoms that have 1 sigma and 2 pi's.
That one right there.
Carbon dioxide, that doesn't work,
Oh, yeah.
but carbon monoxide would. Because then you would have that sigma and 2 pi's. Another one that would work, dinitrogen. It has a triple bond. So if we put, the question then is, in my mind, one sigma and 2 pi's. So if you have something like this, 1 sigma and 2 pi's, the pi's are formed from unused p orbitals. This one is formed from sp, but that's only one bond, right? So where does the other one go? Well, the other one goes over here. Not bond. So this is an sp over here, that's an sp over there. And these are overlapping unused p orbitals. So you get overlap here, you get overlap here. Right, because we formed the hybrid from an S and a P, right? So we have to have 2 of them, right? One of them goes this way, one of them goes that way. And this one contains a lone pair. That's an example of a hybrid orbital that it contains a lone pair rather than bond. Okay. So that was number 60. Let's see if there are any other short answers that we need to deal with before we go back into multiple choice. How about 58? Stop me if you have questions. Let's see. We'll save brown for special occasions. Okay, for 58, consider the structure of glycine. All right, so glycine is that, and you've heard of amino acids, haven't you? They make up proteins. Okay. This is the simplest amino acid. Okay. There's the amino and there's the acid. Okay. That's why they call it amino acid. Okay. And they've numbered the carbons. That's number 1, that's number 2. Okay. Indicate the hybridization of each nitrogen and carbon atom in the molecule. All right, so for A, we've got a table set up for us. And this is A part. And we've got a first carbon, second carbon, nitrogen. And we want hybridization for each one of those. Then we've got a B part and a C part. We'll do the A part first. Indicate the hybridization of each. All right. So let's see. 2, 4, 6, 8, 2, 4, 6, 8. We've got all those. Now, the carbons are going to be easy because you've got 3. 1, 2, 3. So you need 3 sp2s. I need 3 hybrid orbitals, and they have to come from 3 atomic orbitals. So 1, 2, 3. Okay, so this one's sp2. This one is 1, 2, 3, 4. I need 4 of those. sp3. Okay, nitrogen's trickier. Nitrogen, you have to know, let's take it down here. You got a hydrogen and a hydrogen, but that's not everything. If you draw the Lewis structure, what you'll get is 2, 4, 6, 8.
Do you not include the carbon?
Well, we're talking about hybridization for nitrogen. Okay, so nitrogen is going to have 1, 2, 3, 4. That lone pair counts. So nitrogen is also sp3. Okay, B. What is the total number of bonds in the molecule? Well, just count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I have 1, 2, 3, 4, 6, 7, 8, 9, 10? 10 bonds. Okay? See if I did that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Why don't you count the one? Is that just a one?
Where? Here?
Yeah.
No, those are numbered carbons. Those are just the numbers. First carbon, second carbon. They don't mean bonds or anything. So around that carbon, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. Where did I get 10 bonds? Hold on a second. Let's draw this whole thing out. One, 2, 3, 4, 5, 6, 7, 8, 9. 9 bonds. Isn't it?
Count the H and O together.
Thank you. That's where we got 10. You're right. 10 bonds. How many lone pairs around oxygen? 2. So that means oxygen has a octet, 2, 4, 6, 8. 2, 4, 6, 8. This one also has 2. 2, 4, 6, 8. Oh, and C is the number of pi bonds. So how many pi bonds do we have there? How do you count pi bonds? Well, you subtract out all the sigma bonds. Sigma, 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 sigma. 1.
Wait, I thought you can only have one sigma, or is it just one sigma between the two bonds?
Just one sigma. Right? There's one sigma here, but there's also a pi. Sigma on that side, pi there. The rest of them are sigmas. There's only single bonds. A single bond is always just a sigma. A double bond is 1 pi. A triple bond is 2 pi's. Okay? So this would have what?
2 pi's and 1 sigma.
Right. There'd be a sigma there and a pi there. Yep. So that was 58. Let's see. About 57. It's going to take a little doing. And I think work problem should have 57. Okay. No, it's 56. 57. 57 and others use this specific type of notation. So we take that that energy chart for the molecular orbitals, and we just take it and turn it 90 degrees. So how do we know for, let's see, hydrogen? Let's see, let me get them all up there. We've got dihydrogen. We've got cation of dihydrogen. Got the anion of dihydrogen. We've got cyanide ion, cyanide molecule, and the cyanide cation. Okay. So, in order to determine, to answer the question bond order, we've got to know what their molecular orbital structure is, right? This one's simple. It's a sigma derived from a 1s, right? That's it. Why? Because even though we have sigma star, we don't have any electrons for it, right? We've only got 2 electrons. They go in the first one. What if we subtract an electron from that one? 1. Right. Okay. If we add 1, now we need the sigma star. Okay. So that's how you put the hydrogen together. How about the cyanide? Well, the cyanide, we're combining carbon and nitrogen. And remember, the homonuclears to the left of this point have sp mixing. So if you form a heteronuclear from 2 that normally would be homonuclear mixing, their product is going to be mixed. So the CN here would be a mixed situation, and if you look at, we just take carbon or nitrogen, it doesn't matter which. Let's see, the very last page. We just take nitrogen. So we're going to have 2s sigma. We're going to have a sigma star 2s. We're going to have a pi 2p, a sigma 2p.
Are you just going till C2 and N2 mixed together? Or like
Yes. Right, from the chart.
you're adding up to one, adding up till they.
Well, I'm building the molecular orbital structure first. We haven't put any electrons in them yet. But you can use either carbon or nitrogen because they're both mixed. Right, so it doesn't matter which one. But you do want to count how many electrons. So valence electrons for carbon would be 4. For nitrogen would be 5. We need 9. Plus 1. So this has 10 electrons. This one has 9 electrons. This one has 8 electrons. So this one will be 2 here, 2 here. We actually have 2 of these, right? So you can have 4 electrons in that one. 2, 4, 8, and then 2. Okay. So if we do this one, and then this one, see why we have 4 here is because you have 2 pi orbitals. Right? When you look at the diagram, there are 2 pi's there. We just put them together here. We didn't split them out. Okay. So we've got 9 electrons here. 2, 4. 4 is 8. 1 is 9. And then we subtract one more, and that one's gone. Okay, so there are your structures. Now, bond orders. This is 2 minus 0 divided by 2 equals 1. This is 1 minus 0 over 2 equals 1/2. This is 2 minus 1 over 2 equals 1/2. Okay? So it's 1, 1/2, 1/2, ABC. D, we have 4, 6, 7, 8 minus 2 divided by 2 equals 3. This one is 2, 6, 7 minus 2 divided by 2 is 2.5. And this one is 6 minus 2 divided by 2 is equal to 2. So there are your bond orders. 1, 1/2, 1/2, 3, 2.5, and 2. The trick to doing this one is to recognize that this one's easy. Is to recognize that both of these come from the mixing side. So when you combine the two, you're going to use a mixed orbital structure. Okay, that's the trick. Then just count up electrons and fill them in. That's the easy part. Setting up this properly, that's the trick to doing this one. Well, let's see. Got any more short answers? What's wrong with that? Okay, got that one done. $56, I'm gonna leave that one up there. Because 56 asks which one of these are paramagnetic. So remember, paramagnetic is unpaired electrons. Through I. C, D, E, F, G, H, I. Okay, we've got O2, O2 minus, O2, 2 minus, B2, C2, N2, F2, Cn minus, and P2. All right, so that's homonuclear. All of them are homonuclear except for this one. So you would have to do that one fresh, like this one. Right? So if you draw this one out for Cn minus, you find that all the electrons are paired. 2 pair here, 1 pair there, 1 pair there, 1 pair there. So that one is diamagnetic. All right. How about P2? That could give some people problems. Well, P2 is going to be just like N2. Right. So since P2 is not in the diagram, and I just look at the, here we go, look at N2. N2 is all paired. P2 will also be paired. The difference between P2 and N2 is that P2 is constructed from 3P, 3S, 3P orbitals. N2 is constructed from 2P and 2S orbitals. So N2 is also diamagnetic. How about F2? Well, just look at the chart. F2, they're all paired. Right? And that's going to be on the test, right? The only one that you have to deal with individually is the Cn minus. The rest of them are on the chart. C2. C2 is all paired. How about B2? B2 has unpaired, so it would be paramagnetic. O2, this one, let's do that one. O2 has unpaired. Okay, now look at O2 and add an electron. Where is it going to go? Right, but you still have an unpaired, don't you? So that's still paramagnetic. How about 2 minus? Right, because it's going to pair up with both of those unpairs. So let me see. That was 56. I have to check my answers to be sure I didn't make a mistake. So, yeah. So out of that list, this one, oops, wrong one, sorry. The paramagnetic. Here we go. This one, and this one are the paramagnetic. Okay. So actually, we've done all the short answers out of that document. We're doing on time. Coming up on 9:26. And the lecture runs until 10 something. 30. Yeah, okay.
We're not gonna use any last time. We're not gonna finish both.
We probably won't have to use lab time.
That's the question. I didn't
Yes.
know this earlier.
Sure.
All you said is I would write down. Earlier on 57,
Uh-huh.
when we had CM negative charge, we had pi 2p equals 4. When we wait, never mind. I answered my. Never mind. I messed up. I confused myself. Never mind.
Yeah, okay. All right. That one right there will stick in your mind. That's funny the way the brain works. The ones that you struggle with the most, those are the ones that stay with you. Let's have something to do with the synaptic pathways, reinforcement. I have to ask Joycey about that one.
Probably too much drama. Yes, probably too much.
Oh, too much drama. Yeah, right. Sorry. The operative word starts with a D.
Too much drama.
Okay. Let's do this one just to see if we picked up anything on that previous. Consider this structure. Okay. Okay, and the carbon's labeled. We're only going to label this one, this one, this one, and this one. 1, 2, 3, and 4. What's the hybridization of these 4? Oxygen, C1, C2, and C4. Okay? All right. To do oxygen, you need to know the Lewis structure, right? And the Lewis structure has two lone pairs. So actually what you're dealing with is 1, 2, 3, 4. So this one is sp3. This carbon is easy, 1, 2, 3, 4. This carbon is 2, sp, it's linear. And this carbon is 1, 2.
Why is that one linear?
Oh, because it has 2 electron groups. From the VSEPR model says it's linear. Okay. Because this is hybridization. And that's still the localized electron model, which incorporates
That's for,
VSEPR. Yeah. And this one is 1, 2, 3 groups, which means trigonal planar, right? So it has 1, 2, 3. So sp3, sp3, sp, and sp2 would be A, is the answer to that one. The real trick here is oxygen, recognizing that it has 2 lone pairs, right? It's not linear, right? It has 1, 2, 3, 4 electron groups. That makes it sp3 hybrid.
if it was linear, you just have to be.
Yes. This is sp, 1, 2 groups. Okay, that was 3. This is a good one. Let's go back to 1. Brain teaser. Atoms that are sp2 hybridized. They're sp2 hybridized. How many pi bonds can they form? Well, consider, how many p orbitals do you have to work with? You got a px, a py, and a pz. And then your s. We're taking 2 of these to form sp2, right? So you have left over an unused p orbital. So an unused p orbital means you have the potential for a pi bond, just one pi bond. So that's why B is the answer for 1. B equals 1 pi bond. While we're on the subject, what if it's sp hybridized?
We have 2 pies available.
Right. We have 2 unused p's, so you can have a pi for each one. So that'd be 2 pi's.
Would it make a difference if it's like 2 SP? The pies? Would that change anything?
What, right here?
Yeah.
Well, you would have 2 sps.
I mean, like, would it change anything for pies?
No, it wouldn't change anything for that. Those are just unused p orbitals. So they're available for overlap on a pi. Let's see. That's page 1. Let's see here. What if we do, let's do 7. This will require a Lewis dot structure. We're starting with this one, right? And we want to know the hybridization for the bromine. So you need the Lewis dot structure to tell you what the VSEPR is. right? So bromine is 7, 3 times 7 for fluorine is 21 equals 28. So put the bromine in the middle, put our fluorines around, 2, 4, 6, 22 electrons, okay? 4, 6. So 6 around each of the fluorines maxes them out. So 3 times 6 is 18, right? That's 4 electrons. 4 electrons left over, they have to go on the bromine. Okay? Yep.
Why couldn't you have like a vent kind of model, the F's, does it have to be straight out?
Oh, that's just for the purpose of drawing the Lewis dot structure. Yeah. We haven't gotten to the geometry yet. Okay. So we've used up electrons here. We have these 2 pairs left over. So around the bromine, we have 1, 2, 3, 4, 5. 5 electron groups means what? 3 in the middle.
Oh, TSP3.
1, 2, 3, 4, 5, which would be 5 trigonal bipyramid. That wasn't the question. Actually, hybridization was the only question, which was D, DSP3. That's right. Okay. Number 8, I think I've determined that's a bad question. I'll give it to you. But it's really hard for you to figure this one out without understanding the terminology. Tetracyanoethylene. Tetracyanoethylene. So, since you've never had organic chemistry, that doesn't mean anything to you. I acknowledge that. But you're given this skeletal structure. Okay. Now, if we were to draw the Lewis structure for these, we would see that we have 1, 2, 3, 4, 5, 6 carbons and 4 nitrogens. So there's the molecular formula. And there are no hydrogens in this molecule. None at all. If there were, I would have put them in there. So this gives us 24 electrons there and 28 here, right? No, 20. 5, 4 times 6. Yeah, that's right. So that's 44 electrons. Okay, so if we say 1, let's say 2, 4, 6, 8, 10, 12, 14, 16, 18. We've used up 18 already. 26 electrons that we have to deal with. We start from the outside in. 1, 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And then where's the 26 go? Now you could put them in here. Or you could put them, if you work from the outside in, you'd have to put them here. But that would work in the middle. Yeah, the middle would be best. Yeah.
Question: where did you get the 18 thermal bit? Oh, no, never mind. I see the bonds.
Okay, so now we've got to make octets. All right. We only need 1 more for this carbon and 1 more for that carbon. So if we move this one over here, that gives us a double bond. So that's 1, 2, 3, 4. So these central carbons, that gives them octets. How about these out here? Well, the only way to give this carbon an octet without destroying the octet for the nitrogen is to move these over like that. There. So that gives you 1, 2, 3, 4, 1, 2, 3, 4, because you have that extra lone pair. So if you do that for each one of them, that gives you, and now you only have one lone pair left over for each nitrogen. So that's going to be the structure for tetracyanoethylene. This is the cyano group. Tetra means 4, 1, 2, 3, 4. Ethylene means you have one double bond between the carbons. So that's the ethylene part right there. Not that you have to know that for the test. But then the question is, how many of the atoms are sp2 hybridized? So sp2 hybridized is what? Trigonal and planar. Need 3 groups. So which ones have 3? Well, that's only got 2, 2, 2, 2. This is the only one that has 3. You've got 3 here, 3 here. So you have 2 sp2 hybridized groups, which is A. Okay. After you've had organic chemistry, right, everybody's going to take organic, right? I'm joking. After you have organic, you can take the name and draw the structure. Right, you don't have to go through all that other mess. Draw the structure, answer the question. It'll be just like that. But since you don't know what the name means, then you need the structure and you need all that rigmarole in between. Let's see. This one might give you some trouble too. 11. So you have these 3 structures. Cyclic structures. Now I'm going to have to explain what that means. Anytime you have 2 lines coming together in organic chemistry, that's a carbon atom. We don't write carbon atoms in organic structures because it gets too messy. We don't write hydrogens either. Right? So what that means is if you got a carbon there and a carbon there, and the rest of them are hydrogens, then you would have a hydrogen there, 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 and there. Right? So it's 1, 2, 3, 4. Around each carbon has its 4. This one, there will be 2 hydrogens here, 2 there, and then 1 for each of these. And this one has 1 here, 1 here, and 2 here. Okay? So now the question is, which molecules have at least 1 carbon atom that is sp hybridized? So sp means what? Linear. Are any of those carbons linearly arranged? No. You've got 1, 2, 3 groups here. That's sp2. All of them are sp2s.
Matt, good question. How come over the bottom?
I just saw that. This one has 4, so it's sp3. And these are also sp2 again, right? So there are no sps there. These are all sp3s. These here, and these are sp2s. So the answer is none. None of them are sp hybridized. They can't be linear. You can't strain that molecule enough to move this molecule, move that in there and make a triple bond. You can't have a linear in a cyclic structure like that. It's physically impossible. Okay. Let's see. Let's do a memory check on this one. 16. You're given this molecular orbital structure. It doesn't matter what molecule it comes from. But if you have that, and then 1, 2, 3, 4, and then this one from a P, this one, 2P. Which one of these statements is true? First of all, since the question has to do with magnetism, we want to look for unpaired electrons, right? So, paired, 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 right? How about this one? Right, because there are two of them there, right? So it's paramagnetic. Then how many unpaired electrons? We have 2 unpaired electrons. That's why the answer is B. It's paramagnetic with 2 unpaired electrons. Okay. The rest of those just requires that you draw the structure and deduce. Let's try xenon pentafluoride, 19. Take this one, charged. What's the hybridization on that one? Well, we can't just draw it like that. We got to know the Lewis dot structure. So for xenon, it's 8 because it's a noble gas. And then 5 times 7 is 35, minus 1 because it's plus, right? So that's 7 plus that is 42 electrons. Okay, now we can draw the structure. 5 fluorines, 2, 4, 6, 8, 10. 32. All right, so if we do 1, 2, 3, 4, 5, 6, 6 times 5 is 30. Leaves 2 electrons. Okay, and the 2 electrons go here. Okay, so now we can say something about the hybridization. 1, 2, 3, 4, 5, 6 groups. Which says what? Octahedral. Which says what? sp3, 3, 4, 5, 6. Okay? All right, so the rest of those on that page, work them out exactly the same way.
So if they didn't have a like, if they didn't have a long pair, it would be a 5 electron group.
Let's see. If it were neutral, it would have one more electron, and it would have a lone pair and an unpaired electron. That would be a problem, wouldn't it? That's probably why we didn't do that. Because it would be beyond. My guess is that it would require some more finagling. You know, pure straight hybridization would not answer the question. Yeah. Oh, we could have gone, if you say that unpaired electron, like that, would give you not 6, but 7, then you would have to go to and you'd have another orbital for that unpaired electron. That's the way I would approach it. And then you would have a structure that we haven't talked about. You need 7 positions. That's why I stopped at octahedral. That's really as far as we want to go in this class. Okay. Let's see. What about 25? The question is, which of the following substances contains 2 pi bonds? Okay, we've got these to choose from. C2H4, C3H8, C2H2, C2H6, and CH4. We'll start with the one we know, methane, right? Methane is sp3 hybridized, right? It's tetrahedral. So there's no possibility for pi's in that one. How about the one above it? C2, C2H6, C2H6. 1, 2, 3, 1, 2, 3. That's also sp3 hybridized. Right, because 1, 2, 3, 4 groups for each one. Both carbons are identical as far as hybridization goes. Then we can go to this one, C2H4. So we do this one and take 2 hydrogens away. So we've only got that many hydrogens. And you can look at it as if you remove that hydrogen, you remove this hydrogen, well, each hydrogen takes a proton with them, right? One electron, excuse me, and one electron stays behind. And these 2 electrons then pair and form that bond. Right? Instead of the electrons making a bond with another hydrogen, they pair and make a sigma. I mean a pi. That only has 1 pi, right? So it doesn't answer the question. This one has 3 carbons and 8 hydrogens. So there's 3, 4, 5, 6, 7, 8. They're all full. That's sp3 hybridized. This one, each carbon is sp2 hybridized. So that means 1 pi. Now, this one, I have to go over here. Right? If we're going to make an octet for this carbon, we need 2 pi's and 2 pi's for this one. So this one is sp hybridized and it has 2 pi's. That, by the way, is acetylene. I'm gonna find something new. I don't know what the numbers are, but I think these came from the version 2 that I'm about to do. Suppose you have this molecular orbital structure.
Is this a certain question or you using that?
This is not out of version 1. I think this one came out of version 2. And this one, pi star 2. Sure, I got them all up there right. Okay, this one's simply, what's the bond order? Right, when you draw it this way, it's not as easy to make mistakes, right? Remember those mistakes that I was making with that energy diagram? Because it was just too much, it was too much drama.
Too much drama.
This one is a lot simpler when you draw it this way. Now you can say this is bonding, so 2, 4, 8, minus 2, 4. There you go. There's your bond order. If you can draw the structure the molecular orbital structure this way, it really makes doing the calculations easier. Okay. Oh, this is a good one. Okay, as the bond order increases.
Is the number 2 again?
Yeah, probably. As the bond order increases, what happens to the bond energy and the bond length?
Does the bond energy decrease, the length decreases?
Exactly. The bond energy increases and the bond length decreases.
The stronger it gets, the shorter the length.
The stronger the bond, the closer it draws those nuclei together. Yep. Sorry.
No, it's fine.
Let's see here. Yeah. Not sticking though. Temperature's right at freezing, isn't it?
I think it's a little bit over. It's 35.
Okay. Okay. Check some here. This one, which of the following has a bond order of 1.5? You have this one, this one, this one, and this one. Okay. So, since you're going to have the you're going to have this information for you on the back sheet. You can do the bond order of this one. O2 is going to be sigma 2s, sigma star 2s, sigma 2p, pi 2p, and pi star 2p. There we go. And then you say, how many electrons does that have to go into those orbitals? Well, oxygen is going to have 6 each, minus 1. So that's 12 minus 1 equals 11. So 2, 4, 6, and then you can have 4 more, 10, and then 1. Okay? And if you do the same thing for this one, you've got 1 extra, so that's 13 electrons. Because you start with 12. This one we took away 1, this we add 1. So this is going to be 2 there, 2, 4, 6, 4 is 10, and then 3 for that. Okay? And then N2 uses the same structure, only N2 has 5, 10 electrons, right? We have 2, 4, 6, 10. And then carbon is using the same structure, right? Because they're all, well, no, excuse me. No. I'm sorry. Nitrogen uses a different structure. Carbon uses the same structure. So we can go ahead and do carbon. Carbon is 8 electrons. And nitrogen is 10. So carbon would be 8. 2, 4, 6, 8. Okay. Nitrogen, well, nitrogen's supposed to have mixing too. Oxygen doesn't have mixing. That's it. Carbon uses a different structure. Carbon and nitrogen use the same. Okay. So nitrogen is, and star 2s. Then we have pi 2p and sigma 2p. So that's 10. 2, 4, and 4 is 8. 2, 4, 6, 10. And then carbon uses the same as nitrogen. And it's 8. 2, 4, Okay. Now the question is, which one's bond order 1.5? Well, you gotta calculate each one. So this one's 2, 4, 8 minus 3. Divided by 2. So what's that? 5 divided by 2 is 2.5. Okay. This one is, oh, we've done nitrogen before, it's 3. This one is 13. So it goes into 2, 4, 8 minus 2, 5 divided by 2. So that's 3 divided by 2 is 1.5, right? So that one's 1.5. Now let's see if this one is. 6 minus 2 divided by 2 is equal to 2 into 3, 1.5.
Just 6 minus 2 is just equal to, wouldn't it? 6 minus 2 is 4, 4 is 2.
Oh, thank you. There we go. So this is the one. Okay. All right. We got about 25 minutes. Let's see if I can find anything that I haven't covered yet. Let's take this one. Starting with this ion, right? And then we have, we're looking for the false statement.
Is this on our, you're talking about version 2?
Probably version 2. Oh, yeah, it might be in this one. Let's see.
There's a which is following statement is false.
Yeah. Has to do with the carbonate ion. See it.
On 36 or the one that's false, but that's only carbon.
Yeah. Okay, so let's go back to this one. Which one of these is false? Okay. Hey, first. sp2 hybrid on carbon. B, the diamagnetic. C, carbon oxygen bonds different lengths. D, total 24 electrons. And then E, all are true. So that means there's no false one in there. Okay. So the approach I take to this one is draw the Lewis dot structure and find out what its hybridization is first. So let's draw the Lewis dot structure for this one. Carbon is 4, oxygen is 6, 18, and then 2 with a charge. Okay. That's 24 electrons. Carbon, 3 oxygens, 2, 4, 6. Got to put 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. There we go. Okay. Carbon doesn't have an octet yet. Needs an octet. So we would move one of those over like that. And that would give us, actually, give us this. No, it's trigonal planar. Okay. So this carbon is going to be 3, which is sp2 hybridized. Okay. But we know that that this is only one Lewis dot structure. Actually, it's like this. As the charge. There's resonance, right? Because we could just as easily have made this one a double bond or this one a double bond, right? But in reality, all those bonds are exactly the same length. And the hybridization, the sp2 hybrid, makes this trigonal planar. All right, so let's see if we can answer these questions from that. sp2 hybrids on all the carbons. That's true. We can't answer diamagnetic yet. We haven't done that far yet. Carbon-oxygen bonds are different lengths. False. They're all the same length. Total of 24 electrons? Yes. So this one can't be right because we do find one false one. The question is, well, since we don't have anything else to choose from, we found our answer. Right, you can stop there. Test-taking technique, multiple choice. Right. If that one's not true, if we can't use this one, that means all we have to do is find one that's false. There it is. Diamagnetic, let's see.
Couldn't the answer also be E as well? False as well.
Which one?
Couldn't E be introduced as false as well?
Yeah, but technically this is the answer to the question. Because this being false, yeah, got me there. I prefer you put that one. But you could probably argue, if you put E, you could probably argue that one too. In which case I'd be forced to give you credit. You'd have to hammerlock me and make me do it. In fact, all the electrons here are paired. We have no unpaired electrons. And without drawing the molecular orbital diagram, which is more difficult when you have polyatomics, right? But if you look at the electrons, they're either in orbitals, which means they're paired, or they're together around each atom. So I would say that that is definitely diamagnetic. That's not definitive because we haven't done the molecular orbital structure, but it's a good guess. Let's see how we're doing on time. 15 minutes? Okay. We're getting close. Let me see if there's anything else in here that just jumps right out at me. Let's go back to this one. The benzene. This is benzene. And that's one representation of benzene. So the question is, how many of these carbons are involved in pi bonding? How about this one? Yep, got that one. How about this one? Got that one. This one, got that one. So all 6 of them are involved in pi bonding.
What was the thing we're doing again? And like what stage is
Yeah.
it called?
How many carbons? Pi bond. Okay. So you just look at each one. We know that each one has a hydrogen on it, so it's sp2 hybridized, which means that there has to be at least one pi bond in there because it has an unused P. But the other way is to look at the carbon and say, is it double bonded to anything else? Yes, that one's bonded there. This one's bonded there. That one's bonded there. They're all bonded. They all participate in a pi bond. So all 6 of them are pi bonded. Now, in reality, the molecule is more like that. You don't have special pi bond here, here, and here. You have delocalization. Of the pi electrons. They're really smeared out over the whole thing. That's why benzene is so stable. The more delocalizing you can do with your electrons, the more stable the molecule. Okay, but the answer to that one is 6 carbons are involved in pi bonding.
That's an SP2, not SP3.
sp2, yep. Right. So you get that cyclic structure. Let's see. If I have to draw this. I need to tilt the molecule some. Got tilted on its side. And you have those unused. You have those unused p orbitals, and they overlap like that, and they form that kind of a donut, a double donut. In fact, this is the benzene molecule is a perfect example of a special kind of pi bonding and delocalization called aromatic. Aromatic molecules are extremely stable because of this smearing, the delocalization. And they get their name because most of them, well, the early ones that were characterized as aromatic, they had an aroma. They smelled. Right? If you smell benzene once, you'll never forget it. I mean, I can't describe it, but if you smell it, you'll know it.
You'll know it's benzene.
Yeah. And benzene has been identified as a carcinogen, so we don't use them in the commercial products anymore. At least not once they get to the public. Now, in the manufacturing process, yeah, you might use benzene. But then they're strictly monitored and controlled, and it's almost as bad as using radioactive isotopes.
What
Yep.
would it used to be used in? Just to pump that? Whatever.
Benzene. Paint thinner is one.
Anything consumable?
Yeah. Yeah, some products. Or benzene derivatives. They're fairly common. Toluene. In fact, I think you can still get toluene. It's that benzene with a methyl group attached to it. I know you can get this one. Phenol. You ever, what's that stuff you can spray in your throat that kills the burn? You know what I'm talking about? Chloroseptic. I think it's green. It's green.
Yeah.
It's got phenol in it. What phenol does is it deadens the nerve. So it stops the sore throat. But this one's not very toxic. Toluene is more toxic. And then you have xylenes, which are dimethyl benzene groups. But benzene itself, pure benzene, is nasty.
Have you ever tasted it before?
Well, you know, funny you should mention that. When you smell chemicals, very often what you're doing is not just smelling, you're tasting. Yeah, it goes in here. Olfactories are kind of on this side, and then it just wafts its way down to your tongue. So very often, the aromatic, the very volatile compounds, you're tasting as well as smelling. And there are some things that are, let's see, dimethyl sulfoxide. Oops, that's not it. Dimethyl sulfoxide is a very effective solvent. It's a liquid solvent, but it's so volatile. If I uncap the bottle here, you would instantly smell it over there.
It would go across the entire room.
That fast, yeah. Plus, it dissolves so fast and moves in your system. If you get some on your finger, you'll taste it. You'll taste it in your, yeah, very fast.
Good thing it's not poisonous.
It takes a good bit to be poisonous, yeah. I mean, you don't want to expose yourself to it continuously, but. And it's used primarily for reactions where you need a non-aqueous solvent. Right? Because many reactions, especially organic reactions, if you've got any water in there, they're going to react, right? So some reactions you want to.
React explosively or?
No,
Okay.
no. Sometimes you want to carry out a reaction in non-aqueous media because of water. You don't want water participating. It's like peroxide. Hydrogen peroxide. In water, you know, off your shelf is 3% hydrogen peroxide. You put it on your scratch, it will break down into water and oxygen. But it does so by reacting with water, right? But if you have it in a non-aqueous environment and you shine a UV light on it, what it'll do is it'll split and make a free radical. Splits right there. One electron goes this way, one electron goes that way. You don't have water there to react with it. Now, this is not used that way, but you know benzoyl peroxide in acne medicine? If you put that in a non-aqueous environment and use heat or UV light, it will split and make a free radical. And that's often used as an initiator for polymer reactions. Okay. So aqueous versus non-aqueous is a central theme in organic chemistry. And that's one of the reasons that the concept of Lewis acid and Lewis base were developed. You know, rather than proton acceptor and proton donor, you have electron pair acceptors, electron pair donors. Because then you can use the acid-base concept for non-aqueous media. That's probably a little more information than you wanted. Well, I don't think of anything else that we need to deal with. Unless you're missing assignments. If you're missing assignments, you better get them into them. Because there's only one possible grade for a missing assignment. It's not desirable. Okay. Let's see. I think I have something for you. Let's see. Steffi's not here. Yeah, here we go. So if you go to a blackboard and look at your grades, and you see empty spaces where there should be a grade, that means you need to turn something in. If you go to my grades and you see an item there that has no grade, that's an assignment that you need to turn in.
Does that include the whiteboard that we just submitted? The information?
Yeah, I think I got yours.
I submitted that online like Thursday.
Yes, I'll check. I've got, that's for the molecular weight of the volatile compound.
Yes, sir.
Okay. Yeah, I got yours. I've got Zach Carpenter's, and I got Zach Mull. Those are the only three I have on those. So if you're missing assignments, you need to get them in. If you're missing exams, you need to take them. And I'm good between now and 1 o'clock. 1 o'clock's my next class, so I have free time now if you miss an exam. Okay. Oh, let me shut this down.